So the next speaker is Nathaniel Arkor, and he will speak about the formal theory of theories. Please go on.
Thank you very much. I'd like to start just by thanking the organizers of the conference for arranging it, especially during these very difficult circumstances. And I'd like to thank them also for giving me the opportunity to speak today. So I'm going to start directly with the motivation. So recall that an algebraic theory is an identical objects functor from the free category with strict finite coproducts in a single object that strictly preserves finite coproducts. And this category F here is equivalent to the skeleton of the category of finite sets and functions. Now I'm going to be using the original definition in terms of coproducts rather than in terms of products, as is typical nowadays. But you can just dualize and everything will be familiar. Recall also that a colimit in set is sifted if it commutes with finite products, and a monad on set is sifted co-continuous if it preserves sifted colimits, or if the underlying endofunctor preserves sifted colimits. And these are exactly the same as finitary monads on set. Now it's well known that these two categories are equivalent, and this is an observation that essentially dates back to Linton in the 1960s. Now, this tells you that the correspondence is very old, and so by now it's very well known. However, despite this, it still remains somewhat mysterious. And this is really the motivating question for today's talk. It's why is there a correspondence between algebraic theories and monads? We'd like to see the connection in such a way that it becomes almost obvious that they should be related. And to do this, I'm splitting the talk into two parts. So in the first part, we're going to be talking about the classical monad theory correspondence, so the one between algebraic theories a la Lever and finitary monads on set. And this is joint work with Dylan McDermott. And in the second part of the talk, I'm going to be talking about how we can consider this perspective in a more general setting, in the setting of a two categories and nice structure, so we can reenact the correspondence and prove the classical monad theory correspondence as a special case, as well as other correspondences that have appeared in the literature. So we'll start with the classical setting. So we want to draw some bridge between algebraic theories and monads. And to do that, we're going to introduce a new component, which is the concept of relative monad. Now, a relative monad is a generalization of a monad from an endofunctor with structure to some arbitrary functor with structure. So we're going to fix some functor j from A to E, and this is going to act a bit like the identity functor for our monad. Now, I'm not going to go into the definition in detail. It suffices to know there is a definition. And in particular, when we take j to be the identity, this is just the same as a monad. So you can think of it as some skewing of a monad in some sense to an arbitrary functor or an endofunctor. Now, every monad is induced canonically by two adjunctions, the Cliestly adjunction and the Eilenberg-Moore adjunction. And similarly, every relative monad is induced canonically by two relative adjunctions, the Cliestly relative adjunction and the Eilenberg-Moore relative adjunction. And these are respectively initial and terminal in the categories of relative adjunctions inducing the monad. Now, what's the relative adjunction? Well, it's very similar to an ordinary adjunction. You can see at the bottom, we have this Homset isomorphism. So we have an isomorphism or a correspondence between morphisms from Lx to Y and morphisms from Jx to Ry. And so notice that if we take J to the identity here, this is the same as an ordinary adjunction, but now we sort of skewed the adjunction relative to this functor J, which was fixed. And so we're going to denote this with this triangle diagram in the center. So from the universal properties of the Cliestly and Eilenberg-Moore adjunctions, we have the following in bijection: J relative monads, J relative Cliestly resolutions, and J relative Eilenberg-Moore resolutions. And by resolution, I mean a pair of functors L and R that are J relative adjoint to one another and composed to give a monad. and have the initial and terminal universal properties. So in this talk in particular, we're going to focus on just these first two. Now, the important point which makes this perspective even possible is the following characterization of Cliestly inclusions. So we have a characterization of when a functor is the same as a functor as inclusion of a category into the Cliestly category for some relative monad. So a functor k from A to B is a Cliestly inclusion for a J relative monad if and only if it has a right J relative adjoint and it's the identity on objects. And in particular, this second point should look familiar because being an identity on objects functor is one of the properties of an algebraic theory. The other property is a colimit preservation property, and we're going to see how that fits in just a moment. So first, I'm going to talk about relative adjunctions that are relative to the Unadra embedding. So consider some functor from A to B, and we're going to say that the domain is small to simplify things. In this case, we have an adjunction relative to the Unadra embedding of A, where the left adjoint is given by F, and the right adjoint is given by the nerve of F. And in this way, we can see that every suitably small functor is left adjoint relative to the Unadra embedding of its domain. And conversely, every left adjoint relative to a Unadra embedding is just a small functor. So being a left adjoint relative to the Unadra embedding is not a very strong property at all. However, things get more interesting when we consider colimits. So if F additionally preserves some class psi of colimits, then this adjunction on the previous slide restricts to a relative adjunction where we take the presheaves that preserve psi colimits. And in particular, every small functor that preserves finite coproducts, assuming here that the domain has finite coproducts, is left adjoint relative to the inclusion into the finite product preserving presheaves on A. And this is equivalent to the inclusion into the sifted co-completion of the category A. And it turns out the converse also holds. So every left adjoint relative to the inclusion into the sifted co-completion preserves finite coproducts. And so really we think of these as the same thing. And this is an analog of the adjoint functor theorem. So now we can say that an algebraic theory is equivalently an identity on objects functor that strictly preserves finite coproducts from F, or it's an identity on objects functor which is left adjoint relative to this sifted Unadra embedding, or it's a Cliestly inclusion of a monad relative to this sifted Unadra embedding. And this way we can tell that algebraic theories are in bijection with monads relative to the sifted Unadra embedding. And just to be a bit more concrete, this sifted Unadra embedding is precisely an inclusion of F into set, or the inclusion of finite sets and functions into the category of all sets. So now we have a connection between algebraic theories and relative monads, which are given by this Cliestly characterization, as well as this relative adjoint colimit preservation property. So now we're going to try to draw a connection between relative monads and monads. And we can also do this. So we're going to fix a class phi of weights, and we think of phi as being some class of colimit diagrams, essentially. And then there is an equivalence of categories between the monads relative to the embedding into the phi co-completion on some category A, and the category of phi co-continuous monads on the phi co-completion of A. And in the setting we're interested in, we have that monads relative to the embedding into the sifted co-completion of F are equivalent to the sifted co-continuous monads on the sifted co-completion of F, which is just the category of sets. So these are the same as finitary monads on set. And hence we have now this equivalence between algebraic theories and monads, which is very elementary in a sense. In particular, we haven't made use of any monadicity argument. It proceeds directly from the definition of algebraic theory and from monad. Now, because I haven't mentioned the algebras at all, since I haven't used any kind of monadicity argument, for instance, you may be wondering what's happened to them. Because in the classical monad theory correspondence, we say that an algebra for a monad corresponding to an algebraic theory is the same as a model for that the algebraic theory. So this equivalence between algebraic theories and monads commutes with the process of taking algebras and models. Unfortunately, I don't have time to talk about this right now, but I'm very happy to have you ask this during question time, and I can go into a little more detail about it. Okay, so now for the second part of the talk, I'm going to show how we can use this new perspective on the monad theory correspondence via relative monads to reenact a similar argument in an entirely formal setting. So we'd like to know what the most general setting we can carry out this argument is. And why do we want to do this? Well, there are many instances of monad theory correspondences in literature, and really would like to know that they all follow from a general theorem, because they all have the same shape. They all should be instances of the same phenomenon. As examples, we have monad theory correspondences for enriched categories, such as that of Lucian Wright and of Burke and Garner. We have correspondences for internal categories, such as that of Johnson and Wraith. And we have correspondences for infinity one categories, such as those of Kasiktin and Henri and Meadows. So it'd be nice if all of these could be shown to follow from some general argument. Now, the setting we're going to be working in is this, and I'm going to state the main theorem, and I'm going to deconstruct the assumptions that we have and the definitions. But this will give you an example to keep in mind. So we're going to let K be a 2 category with a factorization system, which we call Resolute. And I'll explain what Resolute means in just a moment. And we're going to let phi be a fully faithful lax idempotent pseudomonad on K. And this intuitively acts as a co-completion pseudomonad. Another name for this is a KZ doctrine. I'm going to fix some object A of our 2 category. Finally, we're going to suppose that every monad relative to the unit of the pseudomonad at A has a resolution. And this means that for every eta A relative monad, there is some eta A relative adjunction inducing that monad. In this case, we can show that there's an equivalence of categories between the theories relative to eta A and the phi co-continuous monads on phi of A. Now I'm going to tell you what these definitions are in just a moment, but the example to keep in mind is when K is the 2 category of categories, the factorization system is the identity on objects fully faithful factorization system. Phi is the pseudomonad for sifted co-completion, and A is the category F, so the free category of finite coproducts on a single object. And yeah, in this case, the equivalent to the bottom of the slide will be the classic monad theory correspondence. Now, again, we want to prove this theorem by splitting it into 2 parts, by drawing this connection with relative monads. Now, the theory of monads in a 2 category is well known. And the theory of relative monads in a 2 category was recently initiated by Lobbyer. And this is the definition we'll be using. I'm not going to actually give you the definition in the talk, because it takes a little while to set up, but suffice to know there is a definition of relative monads in a 2 category, which specializes to the usual notion of relative monads when K is cat. Okay, so I'm going to explain what a resolute factorization system is, which is really the definition that makes this work. So we're going to let K be a 2 category with a factorization system. And by factorization system, I mean essentially an orthogonal factorization system, but whether the factorization is just unique up to isomorphism. I'm going to say that the factorization system is resolute if every factorization of a one cell into E followed by M satisfies the property that E is left adjoint to M relative to the composite EM. Now, this probably looks like quite a funny property. It's probably not very intuitive, so let me give you the reason why this is useful. So if you look at the diagrams at the bottom of the slide, what this property means is that if we have any J relative adjunction for any J, so L is left adjoint to R relative to J, and we factorize the left adjoint into E followed by M, then if the factorization system is resolute, we can shift M over to the right-hand side. So then E is left adjoint to M followed by R. So a resolute factorization system essentially allows us to shift M cells from one side of a relative adjunction to another. So now again with K, a two category with factorization system, which we're now asking to be resolute, we're going to fix some J, one cell, and suppose every J relative monad has a resolution. So for every J relative monad, there is a J relative adjunction that induces the J relative monad. Now we define a J theory to be an E cell that is a left J relative adjoint. And in this case, we can prove there's an equivalence of categories between the J theories and the J relative monads. Now I haven't defined the morphisms of these categories here, but they essentially are the same as the classical setting. Now, the proof of this is very similar to the proof in the classical setting. Essentially, what this resolute factorization system allows us to do is show that the E cells that have this property characterize the Cliestly inclusions for J relative monads. So this gives us the connection between theories and relative monads given by this Cliestly characterization. So now between relative monads and monads. So this works very similarly to the classical setting. So when J is a component of the unit, so E to A of a fully faithful lac-side and potent pseudomonad, then we have an equivalence of categories between the monads relative to the unit at A and the phi co-continuous monads on phi of A. And by composing with the equivalence on a couple of slides ago, we have that the theories relative to E to A are the same as phi co-continuous monads on phi of A. And so this completes the monad theory correspondence in the two category. And although I've skipped the proofs, they're actually very elementary and follow from the same sort of reasoning as in the classical setting. So really, once you have the definitions, things work out very nicely. Now, I should mention briefly that some of you may be wondering what happens to monad theory correspondences where we have more general J, because here I've just concentrated on when J is a component of a fully faithful lac-side event pseudomonad. So when the monads are given by some colimit preserving monads. And although most correspondences in the literature are of this form, there are some correspondences that aren't. And so it's an interesting question to ask about more general J. And again, I don't have time to go into this now, but I'll be happy to answer questions about it later. But in short, we can also get a correspondence for more general J, but it takes a little bit more work and it's a little less clean. So I'm going to use the last few minutes to talk about some examples. So the first question you might have is how common are these factorization systems which are resolute? And it turns out it's not a very strong property to impose. In particular, any factorization system for which each M cell is represented to be fully faithful is resolute. And we have a whole class of examples that are given by the pro-arrow equipments with finite type collages. So these are the pro-arrow equipments satisfying axioms 4 and 5 of Wood's pro-arrows 2. And they're the pro-arrow equipments that are particularly well behaved. And so any such pro-arrow equipment has a factorization system called the surjection inclusion factorization system. And this is an example of a resolute factorization system. And so if we take the pro-arrow equipment of categories into profunctors, this gives us a bijective on objects fully faithful factorization system. And I just quickly want to note that it doesn't matter really whether we take identity on objects functors or bijective on objects functors. There's just a slight difference in strictness, but the argument works in the same way. And this similarly works for enriched categories. So to be slightly more concrete, let V be a bicomplete closed monoidal category. Then we have that VCAT, the 2 category, has a resolute factorization system, which are given by the identity objects V functors and the fully faithful V functors, and has resolutions of relative monads given by, well, both the Cliestly and the Eilenberg-Moore V categories. In this case, we recover relative monad theory correspondence. So essentially in all settings, we have a relative monad theory correspondence. They're essentially the same thing. And when J is nice, this extends to a monad theory correspondence. So in particular, when we take J to be the co-completion under a class of weights for V, we recover the monad theory correspondence of Lucian right. And when we take J to be a dense fully faithful functor with small domain and locally presentable codomain, we recover the monad theory correspondence of Burke and Garner. So although this 2 categorical setting may seem very abstract, we can actually use it to deduce general correspondences in concrete settings that we're interested in. Now I'm going to wrap up here, which will give us enough time for questions. So the sort of key idea that underlies this perspective is that algebraic theories are precisely the Claise inclusions of relative monads. So they're the same thing. There's no difference between them. They're just a different way of writing down the definition, essentially. And from this, we can deduce a monad theory correspondence by extending relative monads to monads. And this is the step that needs some assumptions. So this is why we often work with J to be the unit of a co-completion, because this is a nice setting from which there's always a monad correspondence with relative monads. And this argument is very neat. It doesn't require any complex hypotheses, so it can be carried out in any 2 category with some nice structure, and namely this resolute factorization system and a fully faithful Lax-Eilenberg pseudomonad. And then the enriched monad theory correspondences follow as special cases. And it's ongoing work to check that the internal correspondences and the higher correspondences will also follow from the same arguments. I'm going to leave it here, and I have references on the slide, but these slides will be online, so you can check them later. Now I'll be happy to take questions. Thank you.
Thank you for this very interesting talk. Are there questions or comments first from the audience? Thank you, Natanya, for your beautiful talk. I have 2 comments. The first one is that your definition of resolute reminds me of the notion of Yoneda triangle by that Polish guy. I don't remember his name, but I think you know what I'm talking about. The title of
I know what you're talking about, yeah.
Thank you. And he has this notion of Yoneda triangle, which reminds me of one of the definitions you gave. And then the second comment is that a good test for this framework you developed could be really these restriction categories where we have the notion of partial Lobue theory, and we don't know whether there is a factorization system like yours, nor a Casey doctrine like the one you want. But it's perfect because that is a honest 2 category, which is very far from the VCAT for some V. So it could be a test place, and maybe we finally discovered that there is no monad correspondence. I don't know, or maybe there is.
Thank you for those comments. Yeah, they're helpful. I can comment briefly on the second point, which is that restriction categories were one of the motivations for the 2 categorical perspective, because as you say, it's a very interesting question, and I've worked out some of the details. The problem is there's still some theory of restriction categories that needs to be worked out. In particular, we need to know whether there is a completion of restriction categories. We know there's a co-completion, but we don't know whether there's a completion. And so if we know there's a completion, then we can use some of these arguments, but that still needs to be worked out. But I think it's a very interesting direction. Yeah.
Okay, there is.
Thank you very much for this very interesting talk. I was wondering that how your framework in terms of monad connect with, Adam Meg, Bourseau, and Lac work on sound doctrines, and in particular how, if you can, for instance, characterize the monads which correspond to the case monad in which you will have, which would correspond to sound doctrines, and also how the algebra structure for a given theory would be connected to being a phi flat in the context of the doctrinal way of seeing stuff.
Yeah, thank you for this question. It's a good one. So one thing I didn't mention in the two categorical setting, because I didn't have time, is that, well, in the classical setting, we have a correspondence between adjoints and co-limit preserving functors, and we'd like something similar in the formal setting. And so it turns out we can do this, and in some work in progress with Ivan de Liberty and Factorization, we have a relative adjoint functor theorem in a two category. And in this setting, we can show that certain theories in a two category correspond to co-continuous one cells in a certain sense. So this is how we recover that in the two category. And so in particular, when we take sound limit doctrines, we get such a nice situation. And so we have a correspondence that works the same way as this framework you mentioned. And I very briefly mention how it relates to the categories of models. So we have this characterization of the category of algebras for a relative monad in terms of a pullback over the Cliestly category, or presheaves on the Cliestly category. So this pullback probably looks quite familiar to anyone who studied monad theory correspondences as a definition of the category of models for various classes of monads. And it turns out this is a characterization of the category of algebras for relative monads. And this is how it connects to the correspondence perspective I outlined. And in particular, when we take an algebraic theory, which corresponds to some relative monad, then we can evaluate this pullback. And so I'm going quite quickly here, but essentially, if we work out what everything is concretely, we can show that the category of algebras for the relative monad corresponding to an algebraic theory is equivalent to the finite product preserving functors from the codomain, which is the Cliestly category of the algebraic theory, into set. And so this is a sort of approach we can use to capture the setting you were talking about of these limit preserving functors and sound doctrines.
Okay, we have questions from the audience, Paul? Not from the audience, from non-audience. Paul, could you?
Nathaniel, you seem to have a pretty powerful and modern piece of machinery there. Now, since you're so keen on looking at old papers, you probably know what I'm about to say. It looks like your relative adjunctions and monads, so they presumably take account of multi and polyadjoints and therefore DS disjunctive theories. And when I was involved in that kind of thing, I was brought up by one of the Paris set people, Christian Lair, or running guitar, or one of the who said, "Oh well, we have adjoints for any functor." So I would imagine that you would have a modern point of view on some of the stuff that they did.
Yeah, thanks for that. I can briefly comment. So one of the other motivating examples, which I didn't mention.
Before you briefly comment, let me briefly comment that we are really over the time, and we were always strict on the time, and somehow it's not fair to the other ones. So please comment really briefly.
Yeah, 1 or 2 sentences. So yes, Dier's multimonads and things like this were another motivating example. And in fact, I mentioned it in my abstract, but not in the talk, so I didn't have time. And there is a relationship, but it's a little more complicated than I have time to spell out now. But yes, I hope to give treatment of that as well. So thank you for that comment.
Thank you. And may I suggest that if there are, and there are namely, some other questions that may be answered on the internet and not physically because our time is simply out. Nonetheless, we will have a 3-minute break and start 3 minutes later and stop 3 minutes later, of course.